Hi everyone, I'm Dongruo Zhou. I'm going to introduce our work Stochastic Nested Variance Reduction for Nonconvex Optimization. In this work, we are focused on finding the epsilon first-order stationary point for general finite sum nonconvex optimization problems. We will use the number of stochastic gradient computations to measure the algorithm performance. Before we introduce our algorithms, let's first briefly review some existing algorithms where the updates are based on so-called semi-stochastic gradient VT. As you can see from the table, the algorithm GD and SGD are based on the semi-stochastic gradient VT, which can be regarded as the full gradient and stochastic gradient at point xt. For the algorithm SVRG and ACSG, they use so-called reference points and use it to construct the VT. And as you can see from the convergence complexity, the use of reference points are indeed helpful for the convergence results. Inspiring by the use of reference points from SVRG and ACSG, we introduce our algorithm SNVRG, which is based on the multiple reference points. SNVRG consists of two parts. The inner part is called SNVRG epoch, and the outer part is called SNVRG. At the beginning of the inner part, this algorithm will initialize k+1 reference points x equals to x0 and k+1 reference gradients, which is equal to 0. And at each iteration, the algorithm will update the reference points and reference gradients by some specific update rules, and then it will construct the semi-stochastic gradient VT with the stochastic reference gradients GT and use the VT to update the points xt. For the outer part of SNVRG, it just random choose one iterate from the SNVRG epoch and use it to update the points. For the update rules, we will just take a very specific examples to illustrate the rules, where we take the k equals to 2 and the t1 and t2 as update parameters equals to 2 and 3 as an example. As you can see, there are 3 reference points which are updated by different frequency, decided by the update parameters t1 and t2. And once the reference points x are updated, reference gradients g will also be updated respectively. It is worth noting that at each iteration, only a fraction of reference gradients need to be updated by the update rules, which makes it possible for SNVRG to achieve faster convergence results with the same stochastic gradient computations. We now compare our algorithm SNVRG with the existing algorithms. As you can see, SNVRG is strictly better than the state-of-the-art results, which is achieved by ACSG by a factor of omega of the minimum of n to the power of 1 to 6 and the epsilon to the power of -1 to 3. Thanks for watching.